Look around the tech industry today, and you will see a shared obsession with the boundless, infinite capabilities of artificial intelligence. But when these highly anticipated projects are actually deployed into the real world, a huge number of them crash. And the vast majority of the time, those failures have absolutely nothing to do with flawed mathematics. They fail because of a uniquely human glitch: misaligned expectations. You have a business leader on one side demanding, "Automate this workflow," and an engineer on the other side interpreting that instruction as, "Write an algorithm to maximize efficiency." In the earliest days of a project, those two completely different languages create a massive communication vacuum. Neither side fully understands the other, yet everyone is nodding and smiling in the boardroom. That vacuum is exactly where scope creep thrives and budgets bleed out. Eventually, after months of development, the engineering team launches a flawlessly functioning piece of software that perfectly solves the wrong problem. To survive the AI revolution, teams have to master the unglamorous, often invisible phase of alignment long before anyone types a single line of code. Let's look at how this plays out in practice. Imagine a national energy provider that decides to initiate an AI project to manage and balance its physical power grid. The executives hand down a straightforward mandate: achieve zero blackouts. As a top-line business goal, it sounds great. As a technical directive, it is dangerously broad and vague. If developers immediately start writing code to hit that infinite target without any established constraints, they will inevitably build a system so complex it becomes impossible to deploy safely. This diagram shows the architecture of alignment. To bridge the gap between that broad mandate and the actual code, teams use this specific protocol of restraint, supported by 4 pillars: requirements, dependencies, priorities, and implications. We tend to judge successful software by its endless features, but in reality, successful systems are defined by what their creators intentionally restrict. The first pillar is requirements, translating zero blackouts into a specific metric with 90% accuracy. Next, assumptions and dependencies expose hidden flaws, like a 30-second sensor data lag. Finding this triggers a procedural response: log the assumption, assign an owner, and eliminate the blind spot. If you skip mapping these physical and operational dependencies, you end up training a highly sophisticated neural network to optimize a perfect physical environment that doesn't actually exist outside the lab. By designing exact requirements and mapping every physical dependency, abstract business strategies are forced to survive contact with reality. The third pillar is priorities. It relies on the won't-have bucket to establish limits. We explicitly deny the algorithm autonomy for high-risk decisions. If overloaded, the AI is completely severed from the hospital grid. It cannot autonomously cut power to critical infrastructure. Drawing a hard boundary detailing exactly what the machine won't do protects the project from catastrophic liability. It also builds essential trust, proving to the human operators that the software isn't going to blindside them. With those limits established, we move to the final pillar: implications. This shifts the focus entirely to the future reality of the project succeeding. If the AI effectively balances the daily power load, the human grid operators will suddenly find themselves with hours of excess capacity. That triggers a need for organizational change management and role restructuring months before launch day. You cannot simply drop an automated efficiency engine into a fragile human ecosystem. Defining the strict boundaries of an AI system is the only way to safely integrate it. This complete alignment protocol is a rigid pre-development contract of reality, stripped of the ambiguity found in a standard procedural checklist. When shifting organizational politics inevitably flare up, or executives start demanding unexpected features mid-sprint, this agreed-upon architecture stands as your primary defensive wall to protect the scope. We spend most of our time obsessing over the raw computing power needed to train machine algorithms, yet the most difficult part of technological evolution is actually aligning human intent. An artificial intelligence system, no matter how advanced, will only ever be as stable as the consensus of the people who originally commissioned it. Because code cannot resolve human confusion, it can only execute it at scale.